We're taking a look at standing waves over the last few days. Standing waves, which are waves that form as a result of interference of waves that appear to be standing still, hence standing waves. When one wave goes from one end, reflects off of the other end, comes back, interferes, it normally looks like a random interference pattern. It's not actually random. We could figure out exactly what the pattern would look like, but it would appear random. But at very specific frequencies, resonant frequencies or natural frequencies of the string, the wave appears to be standing still. So instead of forming this crazy, seemingly random interference pattern, what we end up getting is a pattern that looks like this, or a pattern that looks like this, or so on. That's if you have a string vibrating back and forth. If you have, let's say, an air column, maybe you're blowing across the top of a water bottle like we did yesterday, then it doesn't look exactly like this, but it's close. In fact, what it would look like if we could see the air vibrating would be close. The air is vibrating in a way that looks something like this. The only difference here is that at the open end of this air column, the open end of the water bottles we blow across the top of it, we have an antinode. We have a node at the fixed ends of the guitar string, a node at the closed end or the water end of the water bottle, but we have an antinode at the open end. The third scenario is when we have something like a pipe, maybe, blown across the end of a pipe. It's two open ends. Well, we know that we have to have a node at a closed end, an antinode at an open end. So the first one here, the first resonant frequency, this one, will look like this. Antinode at both ends. Now, the length of this string, the length of this air column, okay, the length of whatever it is defined as L. In this case, L is half of a wave. In this case, L is a quarter of a wave. And in this case, L is a half of a wave again. If we rearrange each of these to find lambda, we get 2L, we get 4L, and we get 2L. We know that F is equal to V over lambda, or F is equal to V over 2L in this case. In this case, F would be equal to V over lambda or V over 4L. In this case, F would be equal to V over lambda or V over 2L. Each of these are what we call a first harmonic. The first harmonic for something like a guitar string where you have two ends that are fixed, two ends that are attached. This one is the first harmonic for something like that water bottle that we're blowing across the end of. Can't spell it. Harmonic. It's not a first harmonic, not at all. It's a first harmonic. Where we have like a water bottle, as I say, we're blowing across the end of it. One end is open, one end is closed. This would be the first harmonic that would be formed, the first standing wave that would be formed when we have two open ends. Maybe you're blowing across the end of a pipe, or maybe there's a wind blowing across the end of a pipe, or something like that. Now, in the first scenario, we could have a second, a third, a fourth, a fifth, and so on harmonic as well. The second harmonic would be twice the value of the first. The third harmonic would be 3 times the value of the first, and so on and so on and so on. For the second scenario, we can have a first, a third, a fifth, a seventh, and so on. But we can't have a second harmonic or a fourth harmonic or a sixth harmonic. The third harmonic, by the way, would be 3 times the first. The fifth harmonic would be 5 times the first. Okay? No. The second harmonic can't exist when you have one closed end. We call that a closed air column, and there is physically no second harmonic produced. You can't get a standing wave produced at twice the frequency of the first one. The next one you can get is 3 times the value of the first one. And we define the 3 times the value of the first one as the third harmonic. Okay? So it doesn't matter what you do. You can do all the mathematical manipulation you want. You physically can't get a standing wave produced at twice the frequency of the first harmonic when you have a closed air column. Okay, go back to the third one now. That's the open air column, open at both ends. Once again, we can have the second, the third, the fourth, the fifth harmonic, and so on. The fourth harmonic would be 4 times the value of the first. The second harmonic would be twice the value of the first. We can have all of them. So where's the pattern here? If both ends are the same, whether we're talking about both open or both closed or both fixed, then we can have any harmonic we want. But if we have one end open and one end closed, two different ends, then we can only have odd numbered harmonics. We can't have even numbered harmonics. Does that make sense? All right. Monday we're going to do an activity with this actually, and you're going to physically find the harmonics of this air column, the sound harmonics, sound wave harmonics of this air column. So remember, when you do that activity on Monday, that there is the first harmonic and the third and the fifth and the seventh, but for that activity on Monday, there is no second or fourth or sixth harmonic, only the odd harmonics for that one. All right? Okay, our homework questions last night were the second part of that worksheet. It was questions 1 to 8 on the second part of that worksheet. Any issues with any of those questions, please? 4 and 8 it is then. Question number 4 says, what's the fundamental frequency of a closed air column? Closed air column. Which one is that? The closed air column. Is that 1, 2, or 3 on the board? Closed air column is which one? It's the second one, right? Closed air column doesn't mean it's closed at both ends. Closed air column means it's closed at one end. It's like the water bottle, right? Closed at one end, open at the other end. So we want to find the fundamental frequency of the closed air column, 22 centimeters long, has an air temperature of 20 degrees Celsius. As soon as we see that temperature, what do we start thinking? The only time you'll use temperature in physics 20 is when you're finding what, Gary? The speed of sound, right? So let's do that right now. Before we do anything else, let's just get the speed of sound out of the way. We know the equation for that is 332 plus 0.6 times T, or 0.6 times 20 degrees Celsius. That works out to be 344 meters per second. All right, good. There's the speed of sound. Next thing we should do, we recognize that it's a closed air column. Draw it. Please draw it. Please don't try to remember an equation. Please don't try to work your way through without drawing a picture. You are statistically, you're way more likely to be successful if you draw this picture. There's the first harmonic. The length of that is a quarter of lambda, and lambda is therefore equal to 4 times L. F is equal to V over lambda, or F is equal to V over 4 times L. We're looking for the frequency. We've got the speed. We just found it. It's 344 meters per second. 4 times the length. Well, the length of it is 22 centimeters, which we have to make sure we convert to meters. Right, Alana? So 0.22 meters. 344 divided by 4 times 0.22, okay, should give us 390, or 3.90 times 10 to the 2 hertz. How many people got that? Good. Good. Perfect kind of question that I could give you on a test right there. Perfect. What if I asked you for the next harmonic? I didn't ask you for the second harmonic. I didn't ask you for the third harmonic or the fourth or the fifth. I asked you for the next harmonic, the next possibility. What would you do? What would you do, Carrie, to find that? Good. You'd multiply that by 3. You'd actually take the unrounded number, whatever that works out to be, right? 389 point whatever, 390 point whatever, and you'd multiply that number by 3. Why 3, Carrie? Why not 2? Because you can't have a second harmonic when you have a closed air column. Got it? I'd remember that if I was you. Okay, I would remember that. Okay, that would be very important for Monday's activity, but it may be very important for something else coming up fairly soon as well. Okay, that you can't have a second harmonic with a closed air column. All right, last question we needed to go over was number 8. This one is an open air column, which means what? Go back to that picture again. Diagram 1, 2, or 3, the open air column. Diagram 1, 2, or 3. Start. Diagram 3, good. So let's draw it out. Let's draw out this open air column. Question number 8. we're already given the speed of sound here, so we don't need to bother calculating that. Draw the open air column, which has an antinode at both ends. Remember that. Node at a fixed end or closed end, antinode at an open end. The length of this is half of lambda, or lambda is equal to 2 times L. F is therefore equal to V over lambda. F is therefore equal to V over 2L. There's my equation. But this time we want to find the length of the air column, not the frequency, like we do in most questions. So let's rearrange this. If F is equal to V over 2L, we got to get the L up by multiplying. The L's on the bottom. Get it to the top by multiplying. F times L is equal to V over 2. Right? All we did is multiply by 2. Both sides by 2. Now we got to get rid of the F. How do you get rid of the F there, Ryan? F times L is equal to V over 2. How do you get rid of that F? Good, you divide by F. So L is equal to V over 2 times F. The speed here is given to me as 341. Hey, but if this is a test, maybe you got to find the speed by using that 332 plus 0.6 times t, which, by the way, only works in air. Okay, if you got a guitar, it doesn't work. Okay, only for air columns. Frequency is 256. Do the math on that one, and the answer's not there. I'm gonna try to do this roughly in my head though. 341 divided by 512 is going to give me somewhere in the range of 0.65-ish. What is it? 66 centimeters. Okay, I predicted about 65 centimeters. How many digits should it be? 3 digits. So 66.0. Okay. Or we'll just say 0.660 meters. If you express that, though, Lewis, in centimeters on a test, that's fine. That's fine. Typically express it in the standard units, though. What you don't want to do, Lewis, is say 66 meters, right? Okay, 66 centimeters would be fine as long as you get your units right. Good there? Right? Can I do 7 as well? Yeah. Seven says, what's the shortest closed air column? You know what might be a good idea? As soon as you start reading the question and you see open or closed, just draw the air column. Don't worry about the actual standing wave right away. Just draw the air column to remind you later on what it actually is that you're using, so you don't make a mistake with that. Closed air column. It will resonate to a sound source tuning fork that has a frequency of 440 hertz. Here's the speed of the sound. So we want to find the length of the air column. This is basically the same as question number 8, except it's a closed air column instead of an open air column. The shortest air column will occur at the first harmonic, and the first harmonic is going to look like this. We've got a node at the closed end and an antinode at the open end. L is equal to 1/4 lambda. Lambda is 4L. F is B over lambda, but lambda is 4L, so F is equal to B over 4L. We're looking for L here. So once again, we're going to take the L up by multiplying. We're going to take the F down by dividing. The speed of the sound is given to me as 341. You could find it if you were given a temperature, but we don't need to here. The frequency is 440 hertz. When we do that math, we should get 0.194 meters. Okay? Does that make sense? You guys comfortable with that? Reasonably comfortable with that? I promise you this. You will get a question on Tuesday's test involving, maybe it's a guitar string, maybe it's an air column that's closed at one end, maybe it's an air column that's open at both ends. You will get a question on this on Tuesday's test. I promise. Okay? I said something earlier in this class that alluded to which one you'd get. I gave you a hint. Okay? So if you caught that, okay, you were right. If you didn't catch that, then maybe go back and watch the podcast if you want that hint. The last topic, and this is a fairly quick one today, is called the Doppler effect. The last topic of this unit is called the Doppler effect. This is the last unit of our year, so this would be the last topic of our year. This is it. The countdown is on. We got 20 minutes left of Physics 20. We just watched a couple videos now with the Doppler effect. One that showed you what the Doppler effect is. As the van was coming towards us, blowing its horn, the pitch seemed high, seemed unusually high. As it was going away from us, it seemed low. When a sound, or any other wave for that matter, is coming towards the observer, the pitch will seem higher than it really is. It's not really that high, it just seems that high. It's the apparent change in frequency of the wave. When it's going away from us, it seems lower. It's not really lower, it seems lower. It's the apparent change in frequency of the wave. Due to what? Well, it's due to either the source, that being the van, in the case of the video that we just showed you, or the observer. Maybe the guy on the side of the road is the one that's moving, not the van. The apparent change in frequency of a wave due to the relative motion, doesn't matter which one's moving as long as one of them is moving, of the source and the observer. Okay, we watched our Big Bang Theory little clip on Doppler effect. This is exactly the definition that Sheldon gave us. I copied it directly from what he said because it's perfect. The apparent change in frequency, not the real change, the apparent change in frequency due to either the source or the observer moving, or both of them moving. Okay? Yes, that's a great question. Great question. Carrie's question, if you didn't hear that, was if you were driving your car around outside at a relatively high speed, I don't mean like 300 kilometers per hour, but 50, 60, 70 kilometers per hour, and there was a loud sound on the side of the road, you would hear the same effect as you drove by it, as if it drove by you. Okay? Because the bottom line is, it doesn't matter whether it's coming towards you or you're coming towards it, the effect is exactly the same, right? Does that make sense? Now, if you're both moving, then it gets a little bit more complicated, right? Because you can still get the same effect, but if you're both moving, it can be more complicated. Let's say, Carrie, if you're moving at 50 kilometers per hour to the north, let's say whatever's producing the sound is moving at 50 to the north. Well, now you're not moving relative to that sound, right? But if you're moving at 50 to the north and 50 to the south, then basically the effective speed is 100 kilometers per hour. So you get twice the effect. Well, how do we predict what effect is going to be? Beyond it's going to be a higher pitch or lower pitch. How much higher? How much of a lower pitch? Well, we have an equation. And I told you this is the last thing that we do in this unit and this year. The bad news is the last equation that we do looks kind of ugly. FD is equal to VW over VW plus or minus VS times FS. Good news, last equation we do this year. Bad news, it's a doozy. Let's look at what these things stand for, and then we'll tell you how to actually use this equation. FD stands for the Doppler frequency. The Doppler frequency is the apparent frequency. That's what you hear, or not necessarily hear. You may have heard of a red shift or a blue shift in astronomy. Okay? That's the apparent shift in frequency of a light wave. It happens with all kinds of waves. Sound waves, light waves, any other wave. It's just that we notice it the most often with sound waves. It's not just unique to sound, though. We just notice it with sound. The apparent frequency of the sound, or of the light, or of the water, or whatever wave it is. The apparent frequency, and that's going to be measured in hertz. That's what we perceive it to be. It's not really that value. That's what we perceive it to be. Fs is the frequency of the source. It's the actual frequency. So if the frequency of that car horn was 400 hertz, it would appear to be 420 when it's coming towards us, or something like that. The apparent frequency, or the Doppler frequency, is the 420 number. The actual frequency, which is what it would sound like if you were sitting inside the car, that's Fs, the actual frequency. That would be the 400 example. The units for that are going to be hertz as well. All right, so far not so bad. It's that stuff inside the brackets that seems kind of ugly. The whole fraction and then the whole plus or minus thing, especially. We still have two more variables to identify, though. VW is going to stand for a speed, right? But suppose Vs is going to stand for a speed. The temptation is to make Vs the speed of sound. But it isn't. Vs is not the speed of sound. It doesn't have to be sound. It can be light. It can be water. It can be whatever. Vs is not the speed of sound. Vs is the speed of, what else starts with an S here? The speed of the source. So in the video that I showed you, it's the van, how fast the van is moving, the speed of the source. And that's going to be in meters per second. EW, on the other hand, would be the speed of the wave. In the case of the van video that I showed you, that would be the speed of sound. In the case of gravitation, or of redshift, or of blue shift, in the case of astronomy, it would be the speed of light. It's the speed of whatever wave it is. Usually, that's sound, but not always. Of course, VW down here means the same thing. It's the speed of the wave in meters per second. Now, the only other thing we got to deal with here is this whole plus or minus thing. You will never put both of those into the equation and use them both at once. It's either going to be VW plus Vs, or it's going to be VW minus Vs. One of the two. Yep. Yes. Yes. One of them, you're going to use a plus and a minus in two different situations. One of those situations will be when the source is coming towards you. One of those situations will be when the source is going away from you. So the first part of the video that I showed you versus the second part. But which is which? If you're anything like me, you should not try to memorize which is which. You should figure it out every time. Okay, let's figure it out. Let's figure out when we use plus and figure out when we use minus here. Okay, answer this question for me, please. If I make this a plus, if I make that bottom a plus, that makes the bottom, the denominator here, VW plus Vs, a bigger number, right? If I add them, the number becomes bigger. If I subtract them, the number becomes smaller. Agree? Agree with that? Okay, so if I make it a plus, that bottom number becomes bigger. If that bottom number right there becomes bigger, then FD becomes what? The Doppler frequency, the apparent frequency, becomes smaller. The bottom number becomes bigger, then this number becomes smaller. So if I add these together to get a bigger number, this becomes smaller. That must mean that the source is going away from me. So let's make that a plus when the source is going away from me. After the van has passed me, not when the van is coming towards me. Now, you can remember that, but in a couple of weeks when you go to write an exam, you're probably going to forget it. And you might remember it this afternoon if you try to remember it now, but you're probably not going to remember it in 2 weeks. If you go through the logic that I just went through, you can go through this in 2 years and still be able to figure it out, not just in 2 weeks. Okay? Figure it out. I make it plus, this number has to be bigger, this number has to be smaller, has to be going away from me. Well, by symmetry then, if I make it negative, then the source has to be going towards me. But let's just make sure we haven't made a mistake with the first one here. If I make this a negative value, that plus or minus becomes a negative value, VW minus Vs instead of plus. This becomes a smaller number on the bottom. A small number on the bottom makes this number what? Bigger. If this number becomes bigger, it must be going towards me. So, don't ever make it both. Don't ever try to do an equation, use an equation with plus and a minus in it. You do one or the other, plus or minus. Make it plus if the source is going away from us. Make it negative if the source is going towards us, okay? Can you do both to figure out what the difference between the two? Yes, you can. So if I wanted to find the difference in pitch between when the van was coming towards me and when it was going away, then absolutely you could. But you do it separately, right? You do the problem of the van coming towards me using negative. Then you do the problem of the van going away from me using the positive, and then you'd subtract the two to get the difference in the frequency. Yep. You already have the actual frequency, right? The actual frequency is Fs, right? In order to find what we just found using with Gary's question there, we'd already have the actual frequency. Yep. The actual frequency? Oh, there's a number of ways you can measure that. There's more primitive ways, like say you're tuning an instrument. Right? You can use a phenomenon called beats when you're tuning an instrument. I don't know if the music people in here know the term, but you probably know what I'm talking about. You pluck a guitar string, you want to tune that guitar string. Okay? You play a piano key, it's supposed to be that same pitch, and if it's close, you hear this wah wah, this beats sound. But if you nail it bang on, you don't hear that anymore. So we've just measured essentially the frequency of that guitar string by comparing it against something else, right? So there's more primitive ways than that. But nowadays you can take out your iPhone and get an app that would measure the frequency of, the guitar string or the frequency of that horn or whatever. All kinds of ways to do it. All right. I don't like the example that they gave us in our textbook, so I'm going to give you my own here, okay? Here's your example. Here's your last example, the last example for new stuff of the year. Let's say a car is moving toward you at 90.0 kilometers per hour and sounds its 400 hertz horn as it moves. The air temperature is 20 degrees Celsius. What pitch do you hear? What pitch do we hear? All right. The air temperature is 20 degrees Celsius. The very first thing that we probably notice here is that we're going to get a speed of sound from that, right? The only thing we're ever going to use temperature for in physics 20 is finding the speed of sound. Lewis, question? As it's coming towards us, right? It's moving towards me, right? So what pitch do I hear and during this question as it's moving towards? Let's find the speed of sound. 332 plus 0.6 times t. Okay, that gives me 344 meters per second. Now, there was VW and there was VS. What would this be? VW or VS? VS is the speed of the source. This is the speed of the waves. This can be VW. The speed of the source is 90 kilometers per hour. I'm going to convert that 90 kilometers per hour to meters per second by multiplying it by 1,000, dividing it by 3,600, gives me 25 meters per second. So the speed of the source is 25 meters per second. The wave will usually be a bigger speed than the source. It doesn't have to be, but it will usually be a bigger speed than the source. The actual frequency, that's going to be Fs. The frequency of the source is 400 hertz. We're looking for the Doppler frequency, or the apparent frequency. what it seems to be, what it sounds like to us. Our equation, once again, FD is equal to VW over VW plus or minus VS times FS. What do you want to use, a plus or minus on the bottom? It's coming towards us. We expect a pitch that is higher than what it really is. So if we want a bigger value of FD, we want a smaller value on the bottom here. Bart, how do we get a smaller value on the bottom here using a plus or minus? Minus. So let's take out that plus and just make it VW minus VS. VW is 344. VW is 344 minus VS, which is 25. FS is 400. Let's do the math there. Follow along on my calculator here. Let's do the bottom first. 344 minus 25. Let's say 344 divided by that number. 1.07. Let's multiply that by 400. Oops. We get 431. 4.3 times 10 to the 2. So what do we hear? It's really 400 hertz. What do we hear? 430 hertz. It should be higher because it's coming towards us. Hey, sorry, I didn't mean to throw that at you. I made a mistake a minute ago. I said the speed of the wave will almost always be bigger than the speed of the source. The speed of the wave won't almost always be bigger than the speed of the source. The speed of the wave will always be bigger than the speed of the source. If the speed of the wave, now let me think about that actually for a second now. Yes, if the speed of the wave is smaller than the speed of the source, then we don't have the Doppler effect taking place. If the speed of the source, if the car is moving faster than the sound, we don't have the Doppler effect. We've got a sonic boom. We've crossed the sound barrier. That's not a Doppler effect problem. So if you get a question, Doppler effect question, which odds are you will on your test, right? The speed of the wave must be greater than the speed of the source every time. Not almost every time, but every time. Okay? What would it look like? Well, if you want to look at this as a like visualize it, okay, whether you're talking about sound waves or whether you're talking about water waves, doesn't really matter. Okay, here's the source. Okay, it produces a wave that looks like this. Okay, it goes out around it. A circular wave goes out around it, right? Well, a few moments later, that wave is out here, right? But this wave is now gone, right? Because it's gotten bigger. But this source is now over here because it's been moving the whole time, right? In the meantime, it's produced another wave like this. So when you're standing right here, okay, whether you're talking about sound waves or whether you're talking about water waves, as this source is coming towards us, the leading portion of the wave that's in front of whatever's causing the sound, the crests are closer together. Behind it, the crests are further apart. That's why we would hear a higher pitch as it's coming towards us, because the crests are higher together. That's why we'd hear a lower pitch if we were standing over here, because the crests are further apart. Now, if this is water waves, you'd physically see that. Right? Does that make sense? Here's one for you, if you're interested. What happens if that source is moving faster than that wave? Well, you don't see exactly that pattern. If the source is moving faster than the wave, you end up seeing this pattern. Looks more like that. When you're standing right here, and it's sound, as this goes past us, what happens? You don't hear anything right now until the sound waves go past us. But when the sound wave goes past us, what do we hear? Boom. Because you get a bunch of constructive interference taking place right here. That's a sonic boom. As an airplane goes faster than the speed of sound, and that wave catches up to us, you hear that sonic wave, sonic boom. Anybody ever gone water skiing or wakeboarding? Probably not water skiing behind a boat that looks like that, but pretend you are for a second. If you're right here in a tube or right here and swimming or whatever, and this boat goes by you, when the wake from the boat goes by you, what happens? You start bobbing up and down like crazy, right? Because there's this wake that's big here and here. That's the constructive interference of these waves. That's the equivalent of a sonic boom, except it's water. Right? The wake of a boat is the equivalent of a sonic boom in sound. That makes sense? Why do you get that in a boat all the time, but you rarely get it when an airplane's flying by? Because the boat is almost always traveling faster than the wave. Whereas in an airplane, the sound wave is almost always traveling faster than the airplane. Make sense? You don't need to know about sonic booms. That was just kind of a question that came about from what you asked, Gary, but if you want to know. All right, your homework, guys. Your homework. I'm only going to ask you to do question number 1 for homework on page 432, please. Question number 1. That's it. Have a good weekend, everyone. Let's get this question done for Monday. We will do our activity on Monday, and we'll have our test on Tuesday.